So this is it. This is the final chapter in our journey together. And as promised, I'm gonna give you some useful things for later on when it comes to the industry and for your professional life. So I'm gonna talk a little bit about the embedded systems in the automotive industry because I'm stemming from there. This is my own experience, and I wanted to share it with you. But this doesn't mean that it's not applicable or you cannot map it to the different industries, application domains. That could be anything from phones to open public electronics, stuff like that. All right, so automotive real-time embedded systems. The biggest trends today are definitely electric cars. And here you're seeing the pics of two models from the Renault car make. And this one is called the Trésor, and it's a sports electric car. And that one is called the Twizy, and it's an urban car for 1 to 2 people. You can see fit someone in the back if they're small, right? And it's destined to be used in the urban cities in where finding a parking space is extremely hard. Plus, well, the idea is to save the ecology and the environment. So even using batteries, electrical batteries and supercapacitors and stuff like that. But I'm not fully convinced that the electric paradigm solution, is the best one. I think we should go back to cycling and walking on our feet. Right, so a lot of constraints, and you should know that 90% of the new functions, implemented in cars, provided in cars, are usually done with software. So you computer scientists and computer engineers, MET students, you have a bright professional career in front of you, and what's true for the automotive industry is also true for any kind of industry today. So software, most of the innovation is software driven. On the other hand, 50% of electronics, 60% of the cost of a car it will stem from electronics. It's an estimation to 2030, but we're getting there real fast. And this is quite surprising, especially if you talk to your elderly, your grandparents, for instance, and you tell them that 30 years ago, for instance, ask them if they had computers in their car, they will laugh, because a car, historically speaking, is a mechanical machine. So what would the computer do in a mechanical machine? But nowadays you can see that we have even more than 80 computer. So ECU stands for electronic control units, and it's a term that is used to describe embedded computers in cars, and also in planes, by the way, in aircrafts. So yeah, computers are everywhere now, and they're very ubiquitous because of the real-time embedded system paradigm. So this is what we call nowadays pervasive computing. So we have computers in our homes, enabling the smart home paradigm, for instance. And 20 years ago, this wasn't the case. We in a car, so we have more than 80 computers that will have some kind of complexity to integrate them and use them. We have more than 2,500 signals, and I'll let you sleep on what a signal means, but you can start what a signal means, but you can start thinking a little bit, what would that be? So a signal could be a variable for something. We'll talk about that soon enough. Most probably, most definitely, they use different buses, right? So to connect the different computers together. Fair enough. So different networks inside a car. And there are some consortiums and some consortia and some approaches to make people collaborate with each other, to work on a common runtime environment. And this resulted in the AUTOSAR approach, and AUTOSAR stands for Automotive Open System Architecture. And if you're interested in the automotive industry specifically, you're gonna notice, for instance, at Value, the job offers, many of them, they mention AUTOSAR. So this could be seen, one aspect of AUTOSAR could be seen as what AUTOSAR is for cars is what Android is for phones, for instance. Get it? So is to get a common platform on which you can develop your own apps. So on here on cars, you can have a common platform on which you can develop your own functionalities. Fair enough? So collaborate in order to be able to innovate. Right? So we can have different software suppliers. So this is complex because remember, if someone develops, so put yourself in their shoes. If one team develop some kind of software and another team develop a different software and they want to talk to each other, so this could be complex because they don't have the same methods, they don't follow the same approaches, etc., etc. And then again, something that we talked about in the OS course last year is the emergence of multi-core computers, processors, so ECUs, because it's in cars. And one of the challenges, remember, from last year is how to distribute the different tasks on the different cores, how to do the load balancing, the synchronization, etc., etc. So yeah, there was a lot of R&D projects on that particular thing, especially in the context of AUTOSAR. But then again, most of them ended in using heavily one of the cores and relying on one of the cores, heavily on one of the cores, and then give small tasks to different cores. Right. Alright, so here is a visual proof using statistics and data from the industry, showing the number of ECUs throughout time up until 2008. And you can notice prior to the 18th century, you can notice 18th century prior to 1988, there were no computers in cars, right? And this is the case of the German OEM. So OEM stands for Original Equipment Manufacturer. And you can see the number is soaring ever, especially starting the 90s, fair enough. And we're way higher here. And by the way, these are the computers that can be found in cars. So these are the ECUs. They do not look like your average desktop or gaming computer. Fair enough. Here's another schematic from a different manufacturer, from a different OEM. It's PSA, and for those who do not know, PSA is Peugeot Citroën, so this is the official name of them. And here you can see on the y-axis axis here we have the number of ECUs, and here on the x-axis we have the different models, the car models, fair enough. And usually for each commercial name, it could be the Peugeot 208 or something like that, there's a reference used inside the company to describe it. So these are the references usually. All right. So what about the color codes here? What do they represent? So here you can notice it's the number of ECUs, the colors, right? So the number of ECUs for each bus type, and these are the different bus types that could be found in those cars and in most cars today. I've already mentioned at the beginning of the course the CAN bus, and this is what we're gonna tackle later in the last lecture and in this course. Fair enough. Alright, so let's talk constraints. The most important constraint is money. It's all about the costs, how to reduce the cost. I remember quite well my very first day at Renault, where I used to work before joining academia, is every 50 cents that we save on one car is millions and millions of euros at the end of the year. Fair enough? Because of the huge number of car units that being sold. So it's all about the cost. It's cost driven approach up until recently, by the way. Another constraint is definitely the safety, right? So there are some safety regulation standards that need to be respected, and such as the ISO 262, sorry, that deals with functional safety of road vehicles. And by the way, some of your colleagues who are working in the on the smart bike project, they're tackling this safety aspect as well, but from a bike point of view. What else? TTM, so time to market. So yeah, it's a constraint, because if we are late, so we would be far behind in the race to new markets, to to suggest to the people new innovations, etc., etc. So time to market is extremely important in this race in order to be a leader. Carryover. So carryover is a formal name to say to describe the reuse of previously developed components and software and hardware, etc., etc. So from one car model to another car model, we can carry over some components, right? Provided that we do the proper integration, testing, etc. Or we can carry over, so we can reuse in the same model from the previous version to the new version. Fair enough? It could be both ways. And the most common projects up until recently were carryover projects in the industry. Of course, legal constraints, because if something happens, well, we need to point out responsibility. So if let's take the the newly autonomous car paradigm, for instance, if a driver or a passenger is sitting in the car and the car is driving itself, fair enough, and an accident happens, so who would be the responsible for that accident? Would it be the passenger or the car maker, the OEM? So there are big questions treated today in Europe regarding that particular issue, and usually Europe takes a lot of time in order to vote laws when it comes to the legal constraints and whether to allow or prohibit using new functions or functionalities when it comes to road vehicles and the aeronautical domain, and even telecommunication and stuff like that. And there are more constraints actually, and more recently, one of the highest constraints is definitely the ecology, right? So we need they've finally got that we cannot tamper with the environment, and we need to do something about it. Alright, so here I'm giving you a schematic to show you different things. You should start recognizing some of the keywords, such as ECU, for instance. So you can notice that there are a bunch of ECUs here, and apparently they're segregated into 4 different groups. So why would that happen? Why would people segregate the different ECUs? A simple answer here is trying to decipher the names. So some of the ECUs are dedicated for something that we call infotainment, right? Other core, other convenience, or other called ADAS. So let's take infotainment, for instance. So infotainment is a word that's made up out of two different words from the merger of two words, information and entertainment. So basically this is anything that would deal with the multimedia in your car, the connectivity to the cloud, to the internet, to the tablets, whatever. Fair enough. And then you have the core auto ECUs. This could deal with anything related to engine control, different parts of the car control, etc. And then something that is interesting and called ADAS. So what would that be? That is anything related to the driving assistance, right? So advanced driving assistance systems, such as lane detections, you figure out that a driver is overlapping from one lane to another, or moving without being conscious, or trying to park the car, helping the driver park correctly, parallel park correctly. It could be anything from detecting the speed limits and forcing the driver not to overpass it, etc. Right? So these are the groups of computers in a car, and then you can see in the red arrows here. So those are the communication channels, and you can see that for the infotainment here, they're basically wireless. So we have Bluetooth, Wi-Fi, some 4 to 5G connections, etc., etc. Alright, however, you can notice that the core, especially the core and the ADAS, are using wired. So why those are wireless and those are wired? To make a long story short, wired, even though that, by the way, remember one of the drivers when it comes to auto manufacturing is to save money. So using wires inside a car, meaning I'm gonna use more copper. I will make my car heavier, because remember, you can imagine that there are a lot of wires inside, up to kilometers and kilometers, by the way. So yeah, at the end of the day, using more wires means that it's going to cost me more. However, the thing with wires is they're safer, right? It's regarding safety. So they're harder to tamper with, they are harder to hack, and they are more reliable, generally speaking. This doesn't mean that there were not attempts to try and use wireless Ethernet, for instance, to replace the wire, and some of them do exist, but I don't believe that they made it to the public. Alright, what else can you see here? So check this out. Oh, alright, so check this out. OEM. So we've heard this word before today. So OEM is the original equipment manufacturer. So why would I have a connectivity between my core ECUs and the car maker? So this could be to log or to debug or something like that. Fair enough? Alright, so have fun deciphering the whole thing, and I gave you a couple of examples. So let's move on to the next slide. Alright, I'm gonna give you an example of the software cost in a car with 3 different phases. So the first phase is the software creation phase, and you can notice that we have the design that's 30% of the total cost here. Coding is 30% of the total cost as well, and then the biggest part is for software testing. So yeah, testing is, and you're gonna notice it when you're gonna apply for jobs and internships and stuff like that. Maybe jobs more than internships is there's a huge need for testing engineers. Fair enough, and this is an extremely important part in that phase. And this doesn't mean that, even though we spend a lot of money in it, doesn't mean that we can be sure that our system is 100% fault free. Fair enough. After the creation comes, so this is done in R&D, comes the production. Fair enough. And here you can see the different costs per 200,000 units. So basically it's it's module 200,000 units. Fair enough. I don't really care about that one. So creation, production, and the last thing is the use, also known as once it's sold and it's out there, it's being used by the users, right? By the drivers. And you can see that the predominant cost here is related to bugs and updates, etc., etc. And I want you to notice something because you need to know about that, because you're engineers, or in the very near future engineers. Alright, so what's OTA here that costs less than 10 millions? So OTA stands for over the air. So this is the type of updates that happen that do not require any any displacement, or you moving to a garage, or moving to the mechanic guy, etc., etc. So it can happen with the internet connection, wireless internet connection, right? So that's an example for this software cost. So yeah, you will have a lot of job offers in the automotive industry when it comes to software. And remember, it's the automotive industry. I'm not talking about app development, something like that. I'm talking about something that is predominantly, historically speaking, mechanical. Alright, so let's talk about the different functions like the ADAS. So the driving assistance systems. So it could be adaptive cruise control, right? So to respect some speed, glare-free high beam and pixel light in order to avoid, getting blind by that. The ABS, the anti-lock braking system, fair enough. So instead of being, slippery, automatic, automatic, automatic parking. So all you have to do is push a button and let the car do the work. Automotive navigation system, night vision, blind spot detection. This is an extremely important one when it comes to detecting the blind spots when you're driving, because you cannot see everything on the road. Collision avoiding systems, crosswind stabilization, so basically trying to minimize the weather conditions, etc. Speed adaptation, lane centering, lane departure, etc., as we talked about. Right, so there are so many of them. You can have fun reading them all and try to research them if you're interested in that. Alright, so I want to show you something now. So, remember the different groups for the embedded computers in a car, for the ECUs. So the ADAS one was one of them. Now I'm going to talk about some functions that are called BCM. BCM stands for body control modules. Fair enough. So these are the things that deals with the body of the car and not the engine. Everything but the engine. Fair enough. So if we check this schematic here, we can first off, we can see AUTOSAR, we can see CAN, so CAN bus and the AUTOSAR logo as well. And so this is the body control module. You can see that it's connected to different components that deal with the lighting, for instance. They can deal with different motors and not the engine, so motors to control maybe the windows and stuff like that. Fair enough. And you can see the different transceivers, so basically the modules that will enable you to connect to a power and to a bus. Fair enough. And here, by the way, this is what we call the EE architecture. This is the electrical architecture of a car, and you can notice it looks like a car because you can see the lights here, the front lights, the headlights. Fair enough. And you see the different things inside of the car and how they're connected together. Anything else? Yeah, so you can here see the ECU is in MCU multi-core, and it's a Norix one, so you can research that if you're interested in it, for instance. Fair enough. And you can see a different microcontroller here that could be used as a gateway. Bon bref, body control, the functions, they are here to supervise and control everything related to the body: lights, windows, security, door locks, access control, comfort controls, etc. Fair enough. An essential and a core function is the ECM. So ECM is sometimes also known as ECU, but it's not the ECU that we talked about earlier. It's not the electronic control unit. It is the engine control module or the engine control unit. So to avoid confusion, I personally prefer to use the ECM acronym and not the ECU. Fair enough. So this could be anything that deals with the control of the engine, right? So to turn it on, off, etc. So to regulate it as well, to maintain it, to maintain the amount of fuel and air, to do the proper mathematical combination and equations in order to optimize the consumption of fuel and to regulate the air intake, etc. Right, in order to optimize the horsepower of an engine. Alright, so here's another EE architecture of a car, a BMW 7 Series, so a fancy one. And here you can see the different ECUs. Some of them are for multimedia here, for instance, so-called MUST in this case. Some of them could be for the comfort, as we're seeing here, so some assistance and safety, and some of them deal with the core, such as the engine control, for instance. All right, and this is the description of everything that you have. So you can see we have 3 CAN buses, one FlexRay bus, so this is another type of bus, embedded bus that could be found in the car, and one MOST bus, and this is a bus that is used for a multimedia usually, and different LIN buses. And by the way, LIN buses are used to connect small modules together. We'll talk about those in a moment. All right, fair enough. All right, so the final thing that I want to talk to you in this recording is the evolution of the electronic control units in cars. So there's a before and after, and the date is 1990. Alright, so before 1990 we had one computer per function, so you can see that as one task per computer, per controller. Alright, so there are some advantages and disadvantages. So let's see the advantages first. Think about them for a second and then try to follow up later. So advantages: integration, because it's not complicated. We're not distributing different functionalities among different ECUs. It's one per ECU, so we're good, right? So easy. We have inputs, outputs, we connect them together. And here you can see it. So function number 1 runs on control unit number 1, and we're good. All we have to do is connect the input outputs to that particular computer, and then there's nothing happening here, right? They're completely independent, no communication whatsoever happening between those. Then second control unit dealing with the second function, and the third one for the function. All right, so this is nice, tidy, easy to implement, right? Integrate and use. What happened in 1990 and what happened after 1990? So let's see. So now we're using multiple ECUs and they talk to each other. Fair enough. So they're connected together using one or more buses, and they're sharing information. And makes sense, because imagine if this function per se is connected to a sensor and that particular computer does not have access to that sensor. Alright, so instead of connecting a different sensor of the same type to that particular computer, fair enough, alright, I can connect the computers together. This one will get the info and share it with the others that need it, that might need it. Fair enough? So we can share information now. Right, so we're gonna use less sensors, less wires, of course less ECUs, because we won't need to duplicate the ECUs and the different things that we need to do. And it would look something like that. Fair enough? So we can use something happening here and go and send it to that particular ECU that might need it. Alright, so all we can do is, instead of having one dedicated computer for a function, we can distribute the function onto different ECUs. Fair enough? So the first function could be broken down into different smaller ones. Fair enough. So you can see that the smaller one, let's call it a component, and this is the vocabulary from AutoSAR, for instance. You can call it a task because you're more familiar with the task. So we can have a big application divided into smaller tasks, and each task could run on a different ECU. So F1, C1, F1, C2, F1, C3, and they talk to each other. Fair enough? And that's the end of it. And next time I'll talk about the different signals and the different buses, and one particular bus in a little bit more details, which is the CAN bus. Fair enough? I'll be seeing you for the last lecture, and that would be the preparation for the final through case studies, more than one case study. All right? So see you soon.